All right, so let's get this class started. On Tuesday class, we talk about there are majorly 3 types of isomerism. They are constitutional isomerism, geometrical isomerism, and optical isomerism. The first one, constitutional isomerism, is it's easy to understand that constitutional isomers, they have the same molecular formula, but differ in the sequence in which the individual atoms are connected, right? And for constitutional isomer, they also have 3 types. The first one is the skeletal isomer, and the second one is positional isomer, and the third one is functional isomer. And for stereo isomerism, it's trickier than the constitutional one, right? And it is majorly have 2 parts, 2 types. The first one is geometrical, for example, the cis-butene or trans-butene, right? The two butene is geometrical is a typical geometrical stereoisomer. And another one is the optical isomer, for example, aniline. If we look at aniline from the wedge perspective, so wedge perspective is to deplete its molecular the configuration in its 3D configuration in space. These 2 lines, okay, here's the mouse. The 2 slim lines are on the paper actually, and just imagine the dash lines stretch back to the paper, means away from you, and the solid lines stretch out of the paper. So what does it mean they are non-superimposable on their mirror image? Is that in order to, we take aniline for example, in order to overlay the 2, we need to flip the right one a little bit, right? Flip to the, so that the carboxylic group and methyl groups are overlapped with each other. And if we do so, we find that the left one, for the left aniline, the aniline on the left, its hydrogen bond is actually away from us, and the amino bond are towards us. And for the one that is being flipped, it's just the opposite, right? The amino group is away from us, and whereas the hydrogen atom is toward us. This is how they are, like, they cannot be completely superimposable to each other. Now, why is this happening? It is because the central carbon atom are connected with 4 different groups, right? Now, if we look at the molecular model here, the sphere in the middle represents for the chiral carbon. And if we try to overlay the 2, this pair of this pair of enantiomer, while C and D bonds, the C and D groups are aligned. However, this A towards us is aligned with B, while this B group is aligned with A, so they cannot be they cannot be superimposed. And these are called enantiomers, right? They are stereoisomers that are non-superimposable on their images, right? This is, we talked about last lecture. And the enantiomers is one type of stereoisomerism. Another type is diisomers, or we call it geometrical isomerism. This is often happening with carbon atom at the double bonds are linked with different groups. These are they can be in trans or cis configuration. Okay, and I had a question for you to consider last class. Is this one, right? Are these in a pair of enantiomers? And in last class, I remember the Christian. Christian, are you there? Hi, Christian, are you there? Have you reconsidered about this problem or any volunteers? How about Faith? Faith, are you there?
Yes,
have you think about this problem?
Laoshi, I think that they are enantiomers because the previous example that was given to us, that was the same way it was. Like we have the A up and it's over here on this side and the B on this side. So I feel like yes, they are.
Okay, that's your answer, right? Okay, any different opinions? Thank you, by the way. Any different opinions? All right. Okay, let's do one thing. If we rotate them a little bit, okay? Let's view from the side where BC bonds are stretched. Like if we view the one on the left from this angle, right? Where the BC bond are stretched out, and view the right one from here. Okay, now we try to imagine this in 3D space, okay? Okay, now we can easily find that this A group on the left is actually aligned with this A, right? If we view them both from the BC bond are stretched, this A is aligned with this A on the right, and while this A group is aligned with this A. So actually, they are completely overlapped, these two, a pair of molecules, right? So they are completely superimposable on each other. So in other words, they are actually the same, right?
Yes.
Oh, yes. Okay, why is this happening? It's actually because if we take a closer look, this is happening only because they have two identical groups connect to the central sphere, right? They have two A's. They each have two A's. Now, if we compare with the previous slide, okay? If we compare with the previous one, we do the same thing. We view from where the BC bonds are stretched. Okay, so we take we look from here, and for the right one we observe from here. Okay, if we do so, and we will easily find that this A group is actually aligned with this D here, right? Am I right? And this D is aligned with this A. So they are non-superimposable actually, right? Just like our left hand and right hand. So what do we call them? We call them enantiomers, right? Okay, from this comparison, we can easily get a conclusion is that the enantiomer exists with only the central, the chiral center is linked with 4 different groups or atoms, right? This is only happening when the central carbon is linked with completely 4 different groups or atoms. If there are 1 or 2 identical atoms or groups linked to the central one, then they are non-enantiomers, right? Okay. So are we clear now?
Yes, Laoshi.
Okay. Now we'll continue. We talk about configuration, but what does it mean actually? So the configuration is the particular arrangement of atoms in space that is characteristic of a given molecule. Okay, so but pay attention, please, because configuration are not the same as conformation. So these two are different. How is it different? The conformation are interconvertible by rotation about the single bonds, whereas bonds must be broken to change one configuration to another. For example, in your last semester fundamental chemistry, you must learn for cyclic organic compounds, there are 2. There can be chair conformation and boat conformation, right? And if you change chair conformation to boat conformation for cyclic compounds, are the bonds broken? No, right? The bonds are not broken when you change from boat conformation to chair conformation, for example. But for configuration, the bonds must be broken to change one configuration to another. Okay, so these are configuration and the conformation are different concepts are actually. Okay. So now we have a better understanding of a pair of enantiomer or the optical isomerism. How do we draw a chirality center or stereogenic center, right? This is easy because this is the molecular model, right? And the sphere is the central, the chiral center here, and the vertical bonds are actually behind this sphere, where the 2 bonds are in the front, which is the hydrogen, which is connected to hydrogen and chlorine. They are in the front. It's actually to see, actually, right? Okay, now we represent this molecular model in form of what the wedge perspective. Like I said earlier, or in last lecture also, the dash bond, just imagine the dash bonds are away from you, like stretch behind of the of the paper, of the plane, and the solid lines are stretched towards us out of the plane, okay? So this is called wedge perspective. We can easily change the molecular model to a wedge perspective. That's easy. We also can use Fisher projection to show the chiral center or a chiral molecule. Now, how do we, how is Fisher projection working? It's the chiral carbon are actually the intersection of the vertical and horizontal lines. So here is the stereogenic center or chiral center, the carbon bond, which is linked with 4 different groups. Okay, so at the intersection. And the vertical lines represent of what? The bonds in dashed lines. So the vertical bonds are bonds that are away from us. And the horizontal lines or horizontal bonds are solid ones that stretch towards us, okay? So this is Fisher projection. Just remember it's derived from the wedge perspective, okay? Okay. Now, another problem is how do we name an enantiomer? How can we look at the two structure and decide if they represent two identical compounds or a pair of enantiomers? How can we name them? For this question, the answer to this question actually has a long history. It predates back to 1956 by chemists Kahn, Ingold, and Prelog. It's called the Kahn-Prelog-Ingold rule. So how does this rule work? The first step you need to assign the priority of the 4 atoms or groups of the atom bonded to the tetrahedral stereogenic center or the chiral center, the chiral carbon atom. If the 4 atoms are all different, obviously they have to be, the 4 atoms have to be different, right? Just like we mentioned earlier. The priority is determined by the atomic number. The atomic number of the atom of higher atomic number has higher priority. Okay. So let me ask you, how is the molecule on the left? Okay, let's do the left first. How is the atom priority ranked for the left, the one on the left? Any volunteers? Tola? Are you there, Tola?
Hello, Shi.
Yeah, can you answer my question?
Can you read the question again, please?
Okay, how do you determine the priority of 4 atom or groups? For this case, okay, they are both groups and atoms. How do you determine the priority of 4 atom or groups for the left molecule? Like which one ranks the highest and which one is the lowest?
The lowest should be hydrogen,
Yes.
and the highest should be the chlorine or something. The Cl. Cl is the highest.
Cl is the highest. How about bromine?
Okay. Bromine then.
Bromine is the first, right? Bromine
Yeah.
has higher atomic number than chlorine. They are actually on the same series on the periodic table, right?
Yeah.
Okay, so which one rank the bromine ranks highest, and
Bromine.
then yeah, and then which one?
Okay, so it's bromine, it's chlorine, it's OH, oxygen and hydrogen, and
Yeah.
hydrogen.
So the OH group, what's the name for OH group? It's hydroxyl, right? Hydroxyl?
Yep.
Yeah, okay. Okay, clear. So for the last one, the priority is bromine ranks higher than chlorine, ranks higher than hydroxyl group than hydrogen, right? Or we can say bromine is bigger than chlorine, bigger than hydroxyl, than hydrogen. Yeah, okay. Thank you.
Okay.
How about the one on the right? Okay, Samira, are you there? Okay, I see maybe the connection is not so well. How about Cyrus? Cyrus, are you there? Hello, Cyrus. Do I read your name correctly? Cyrus or? Yeah, I believe it's. No, Bill? Bill, are you there?
Yes, Laushi.
Okay. Bill, can you tell the priority of the groups or atoms for the right, for this one?
Lower priority is hydrogen. Are you hearing me,
Sorry.
Laushi?
Huh?
The lower priority is hydrogen,
Yes.
and the highest priority is hydroxide.
Okay, so hydroxyl is the highest. How about these two?
What's the meaning for D?
Okay, so here's the question. What does D and T here represent for? Okay.
Yeah.
Okay, I see. So the D here actually represents the deuterium. Deuterium is the isotope of hydrogen, right? Its molecular weight is 2. And the T here stands for tritium. So both deuterium and tritium are the isotopes of hydrogen. And the atomic weight for deuterium is 2, and for tritium is 3. They are
Okay.
isotopes of hydrogen, right? Okay. Therefore, for this case, the highest, the hydroxyl is the biggest. And then what? Tritium, right? And then deuterium. The last one is hydrogen. Okay?
Okay.
Okay, thank you. Okay, so the first step, we need to assign the priority of the 4 atom or groups. And then, okay, if the priority cannot be determined by rule number 1, then we'll continue. It is determined by a similar comparison of atoms working out from the stereo center for example, for this compound here, it is obvious that hydrogen again has the lowest priority, and chlorine here has the largest atomic number, atomic weight, right? So we only need to tell methyl group and ethyl group which one is higher. So in order to do so, let's take a look here to compare methyl and ethyl groups. For methyl group, the second atom connect to the first carbon is hydrogen, hydrogen, and hydrogen. All three are hydrogen. But for ethyl group, the atoms connect to the first carbon is hydrogen, carbon, and hydrogen. So there are one carbon and two hydrogen. So which one is bigger? Ethyl group is bigger, right? Because it has one carbon and two hydrogen compared to the methyl group connecting to three hydrogens. So the priority sequence for this molecule should be chlorine, chlorine ethyl groups and methyl groups, and the last one is hydrogen. Okay, so this is to consider the single bond only. How about the double bond or triple bond? So if a double bond or triple bond is connected to atom A, it is considered as equivalent to 2 or 3 single bonds to A. Okay, so for example, this carbonyl groups. This carbonyl group is with a carbon-oxygen double bond here. So it is considered as equivalent to the carbon atom is connected to 2 oxygen, right? So this carbon-oxygen double bond is considered equivalent to 2 double oxygen single bond. So this means this aldehyde group is linked to 2 O's and two oxygens and 1 hydrogen, while the methanol group here is linked to 1 oxygen and 2 hydrogen. Therefore, aldehyde group ranks higher than methanol group here, right? And the sequence of the hydrogen and hydroxyl, it's easy to tell, right? Hydrogen, again, is the lowest since it's the first atom on periodic table, and hydroxyl ranks higher than both, than the rest of 3. So this priority sequence here is hydroxyl, aldehyde, methanol, and oxygen, okay? So this is scenario for a double bond or triple bond. Okay, so this is the first step. We need to determine the priority of the atom or groups that it is linked to the stereogenic or chiral carbon here. And what's next? We will arrange the molecules so that the groups of lowest priority is pointing away from you, and observe the arrangement of the 3 remaining groups. What does this mean? So the lowest priority group or atom is pointing away from you means we need to place. For Fisher projection, we need to place the lowest priority atom or group on the vertical or horizontal, on the vertical lines, right? Okay. If the ongoing from the groups of highest priority to that of the second priority, then to the to the group of third priority, we go in a clockwise direction. That means to your right. The enantiomer is designated as R configuration. Now this R letter means rectors. The R letter is represents for rectors in Latin language, means to your right. Okay. If the direction is counterclockwise, the enantiomer is designated as an S configuration. So here S, again, it's Latin language, sinister, that means to your left. So to conclude, how do we name tell the configuration of an enantiomer? First thing, we need to determine the priority of 4 groups or atoms that is linked to the stereogenic center. And then we place the group or atom with the lowest priority pointing away from you, and then observe the arrangement of the 3 remaining groups. If it's clockwise, then it's R configuration. If it's counterclockwise, it is designated as an S configuration. For example, here, for this one, the carbon atom is linked with chlorine, bromine, iodide, and hydrogen, right? Now the priority is of the 4 atom is iodide, bigger than bromine, bigger than chlorine, bigger than hydrogen. And now we place the hydrogen, which is the lowest priority, away from us. And we view the remaining 3 groups. It go from iodide to bromine to chlorine, so in a counterclockwise direction. So it's an S. So the complete name for this enantiomer is actually we have a prefix here as chlorobromo iodide iodomethane here. Okay, so we put R or S notation as a prefix of the compound's name. Okay, let's do some exercise. We'll look at this one first, okay? The one on your right lower corner, this one. Is it an R or S configuration? Any volunteers? M-guard? M-guard, are you there? Or you have a Chinese name also? Is Okay, Cyrus, I see you're there. Okay, Cyrus.
Yes, Lao Shi.
Okay. Can you tell if it's an S or R configuration for this compound here?
Mm.
Let's do step 1, okay?
Okay.
Let's
C1.
determine the priority first.
Step 1 is arrow. It's arrow. This will C2H5. C2H5.
Yeah, it's ethyl.
Yeah, SCO. And H is hydrogen. CHTD. CHTD is, oh my God.
So which one is the lowest, ranks lowest? Which one ranks lowest?
HTD, because H2, C2H5, like here you have C2, you have H5, and you have CH3, you have Cl, you have H, you have hydrogen here, you have sodium here, Cl sodium. This one is hydrogen. So C2H5 would be the lowest.
C2H5 is the lowest?
Probably.
Or hydrogen is the lowest?
Hydrogen is the lowest. Oh, sorry, because like it have nothing attached to it. They don't have anything attached to it. Yeah.
Yes, and the atomic number is 1 for hydrogen,
Yeah, it's
right?
1. It's invisible 1.
Yeah, okay. So, okay, hydrogen is the lowest, and which one is the highest?
CH3.
How about chlorine here?
Chlorine is invisible 1. Because chlorine don't have anything attached to it. Or 1, 2, Cl is chlorine.
Yeah,
and, chlorine could be the highest because chlorine dissolves so many particles, you know. Yeah, so I think chlorine is the highest. Probably is the highest.
Yes, like I mentioned before, like I mentioned earlier, their priority rank is determined by what? By their atomic weight or atomic number, right? And here, chlorine, what is the atomic number for chlorine? It's 16.
Chlorine is 16. On the periodic table, chlorine is 16.
Yes. So chlorine ranks highest, right? Because for the rest, carbon, these are carbon. Carbon is the 6th, and the
but it's going to take it's going to take you like IQ to determine, because if you don't know, like chlorine is 16 on the periodic table, because you are not seeing the 16 there. So if you don't know, you are just going to say maybe CH3 is the highest, but chlorine is the highest because it's 16 on the periodic table. Yeah.
Yes. Okay. So chlorine is the highest, and hydrogen is the lowest.
Yes.
And for the rest, we only need to determine.
Yeah, just subtract something like that. You just look at this one from your eyes, just determine.
Yeah, Melcy and Elsie group, right? Like I said here. Okay, let's take a look at this again. Okay, so this one is actually Melcy. This one is actually Melcy group, right? CH3, and this one is Elsie group. Okay, this one is similar to the exercise we just did. Okay, with chlorine rank highest because its atomic number is 16, and hydrogen, for hydrogen, the atomic number is 1. It's the first element. And then we only need to take a look to compare which one is ranks higher, methyl or alkyl group. And for here, they both start with a carbon, right? They both start with a carbon, and for methyl group, the first carbon is connect to 3 hydrogen here, right? Hydrogen, hydrogen, and hydrogen. But for alkyl group, the first carbon is connect to what? Hydrogen, carbon, and hydrogen. So the carbon, the carbon is bigger than the hydrogen here, right? It has 1 carbon and 2 oxygen for this carbon, and for this carbon, it has 3 oxygen. So which one is bigger?
Oh. C1, 2, 4.
Because these 2 oxygen are, these 2 hydrogen are the same in their ranking, right? These 2 oxygen is the same, has the same rank as here. We only need to compare this carbon to this oxygen, to this hydrogen. So carbon, of course, is bigger than hydrogen because the atomic number is 6 for carbon. Right?
Yes.
Okay, clear. Okay. So alkyl group is ranks higher than the methyl group. Okay?
Yeah.
So the priority sequence is chlorine, alkyl group, methyl group, and hydrogen is the lowest one. Okay, so this is the first step. We have determined their priority here. And then what do we do next?
Madam?
Oh, Samara, okay.
Hi.
I hear Samara. Okay,
From my
Samara.
small knowledge.
Yeah.
Hello?
Please go on. Yeah, please.
Yeah, from my small knowledge, R and S is determined by the clockwise or counterclockwise direction. How can we determine that there?
I'm sorry, can you speak louder, please?
The R and S are determined from the clockwise and counterclockwise directions, right?
Yes.
But if it starts chlorine, then ethyl, then methyl, then hydrogen, how can we know? Because it doesn't go clockwise and counterclockwise direction anymore. It just goes.
Okay, I see. I understand your question. So we actually have 4 atoms here, and you're not sure how do we determine if it's counterclockwise or clockwise, right? So we need to put the lowest priority, which is hydrogen here, right? It's hydrogen for this case is the lowest priority, right? We put hydrogen away from us. So this is the Fisher projection. And hydrogen, so the vertical bond here are away from us, and the horizontal ones are toward us. So for this case, hydrogen is away from us, right? Samira?
Yeah, I'm here,
hydrogen, yeah, hydrogen is away from us, right? Hydrogen, we put the lowest, the atom or group which has the lowest priority away from us, and we view the remaining 3. Okay, so in this case, since in this Fisher projection, hydrogen is away from us, and then the rest 3 is from chlorine to alkyl and the methyl groups. Yeah. So it's what, counterclockwise or clockwise? It's from chlorine to methyl and
chlorine.
methyl. Yeah.
The order is chlorine. Oh yeah,
Yeah.
it's counterclockwise. Because the order is chlorine, ethyl, and methyl. Is it? Oh, it's clockwise. It's
Yeah,
clockwise.
it's
clockwise.
it's clockwise, right? So this one is R configuration, right? To your right,
Okay.
right?
Yeah.
We go from chlorine to methyl, to
Ethyl.
ethyl, and yes.
Then
Okay. Okay, now we take a 10 minutes break and we'll continue 10 minutes later. Okay. And we'll do the rest 4.
Okay.